we will now look again at malloc and also another function called realloc. Calloc, as we know now, sets the data to zeros. And if we use malloc, it leaves the data uninitialized. So typically it contains just garbage. But in the beginning of a program, that data is likely to be zeros. So if we use this program, and we can see we allocate 10 ints, and what happens then? We run it, gcc a.c, and semicolon works in the terminal as well. Okay, then we print it, and all elements are zeros without we didn't use calloc, we just used malloc. So why can it be that like that? This is the first time that this program sees this data from the heap. And whenever that happens, the operating system, macOS, Windows or Linux, will set that data to zeros. It's the same both for the stack and for the heap. And of course for global variables as well. Those parts which are not already initialized to something else. And why do we want that? Say one person is logged into a computer and has written a password somewhere in memory. Then somebody else calls malloc and gets that part of ROM as part of its malloc allocation. Then of course it would be very bad if the other person can see the data that was used by somebody else. So therefore operating systems set new data to zeros. Okay. After a while, when we have freed the data and called malloc again, then we get the data that was stored previously. So it's only the first time that the program sees the data that it's set to zero. And why can that be a problem? What I'm trying to say is that there is a risk that we have a bug in the program, but we don't notice it because we get some help, so to speak, from the operating system to set the data to zeros. If we allocate a tree node and we forget to set that to null, in the beginning of the program that may work. And we shouldn't set the tree node to null, we should set the child pointer from the node to null. Then in the beginning of the program that it may work, so that we can check if the child is null and do something. But after a while, when the data that we got for the tree node is recycled and contains garbage, then forgetting to set the child pointer to something may cause disaster. Okay, so even though a program may look like as if it works, it's not at all certain that it does. So what we would like to do is to run valgrind, and like that. And does it say anything that is useful? Let me see. We see all heap blocks were freed, no leaks are possible. That's good news. I mean, we just freed it, but let's see if we have something more serious. Use of uninitialized value of size 8. Okay, what has happened? Somewhere in the printing, this function used 8 bytes. Okay, and discovered that this was not initialized. What Valgrind does is that it emulates a real computer and checks if each bit has been initialized or not. And if it hasn't, it complains. Then the question is, where did we allocate this? I mean, we have made an error and we want to find where that error was made. It's not in the print loop, but the error is that we used malloc and didn't set it to zeros. But that information is not given here. But what it says here, if we use the option track origins, then, well, you can see, we will see where the uninitialized data comes from. So we can use that, and I have already prepared it. So, and what does it say now? Okay, it says uninitialized value was created by a heap allocation, calling malloc. Oops. That's true, but I forgot to compile it with -g. Okay, so let's do that. -g is very useful. It makes GCC or Clang put the line number and type information in a.out. Okay, so let's run it with this debugging information and see if it is nicer. Now it will tell us that it was on line 10. Okay, so on line 10, there was the allocation. So, what can we learn from this? It's the main point is that we should not forget to set data, to initialize data, and to check that we have done it. We use Valgrind. Okay, and the next function, realloc. What it does is that it takes, okay, say we have a pointer and we allocate it, well, we just let it point to an array. Okay. So, and then we realize, so A is pointing here. And then we want some more memory. Then what we can do is to extend that memory, possibly. We call realloc, so we would let that be A, I mean the first parameter, since that's the pointer that we want to get more memory for. And then we say how many bytes we want. Okay, so say we call realloc and use A. This is well, that's not a bad idea, but, and then we can say I'll soon come to what is wrong with saving the value in A, like this. But just we can do that for the moment. Okay, so we want to have more memory, and if realloc can find that, then it just increases the size of this part and returns A again. Okay, so let's assume that this part was used by something else, and we do this again. No, we can say we want 400 bytes instead, and it's not possible to get those 400 bytes just by increasing this, since there is something disturbing us. I mean, this one prevents that from being possible to do. So what the realloc does instead is to allocate 400 bytes and copy what was already, okay, so say this part is just copied from there, and this part will contain undefined data. And then the new address is returned here. Why is that problematic? Okay, what can happen if we use realloc in a bad way? The first bad way we have just seen, but I've not said why it's bad. Well, it's bad because if realloc doesn't find any memory, because there was none left in the computer, then it will return null. Okay, so then we lose this a pointer, since it's overwritten with null. So it's better to save it in something else, like A0, and check if it was null or not. If it was null, then we haven't destroyed A. We have just got that information, and then we can do what is suitable to do when we didn't get any more memory. And if we got memory, we just say A equals A0 and continue happily. Okay, that's one problem with realloc, that we lose memory when we increase it. Okay, I should also mention what happens when with this block, if realloc had to allocate more memory. This block is automatically freed by realloc. Okay, if it found new memory. Okay, but what else can happen? Let's look at another program. So, say we allocate 10 elements, and then we say that B points a bit into this array, and then we and then we do a realloc, and this is bad, as we just saw, because A may be lost. But what happens to B here? B points to the original array, and since realloc may have moved A to somewhere else, this B is then invalid. I mean, if what we saw is that B points to this, and since realloc may have freed that part, this is disaster. Okay, so now you may think that using realloc is a really bad idea, but it's not. If we avoid this problem, having additional pointers a bit into the array, or we should just have one pointer pointing at the beginning of this array in general, then it's no problem. And also we should use a different variable like this. Okay, so when can realloc be useful? For instance, in assignment Word. That's the second assignment. There you will try to find the longest word in the input. Okay, and typically you start with allocating 10 bytes, and if that's insufficient, you can use realloc to extend that, for instance, to double it every time it's too little. And then realloc is really perfect. by the way, the longest word is several megabytes at the test. For the input at Forsete. So it's not possible to use an array on the stack in the word assignment. So realloc is fine to use if we remember these two potential problems. Then I do not encourage anyone to do like as follows, but it's actually possible to skip both malloc and free and only use realloc and calloc. But this is not a recommendation in any way, it's just a reflection. Because if we use a null pointer here and the size, then it behaves as malloc. And if we want to use free, we can set the new size to 0. So then it frees the data. But of course we shouldn't do that. But it's maybe interesting to know that we actually can skip malloc and free. But don't do that.